Okay. Hi, everyone. Today, Nick and I will be presenting about how we scaled the monitoring system at Databricks from Prometheus to M3. So some quick introductions. My name is YY. I'm a software engineer on the observability team at Databricks.
Yeah, hi, I'm Nick. I'm also a software engineer on the observability team.
So for those of you who haven't heard of Databricks, we were founded in 2013 by the original creators of Apache Spark. We're a data and AI unified analytics platform as a service, and we serve over 5,000 customers. We're still a startup, but we've grown pretty big. We have more than 1,500 employees with more than 400 engineers, and with an ARR of $400 million or more. We run across 3 cloud providers in more than 50 regions, and we launch millions of VMs per day to run data engineering and machine learning workloads, processing exabytes of data per day. So in this talk, we'll cover how we monitor at Databricks before M3, and then I'll talk about how we deploy M3 at Databricks, including architecture and migration. And then Nick will cover some of the lessons we learned in this process, including operational advice, important things to monitor in an M3 cluster, and how we do updates and upgrades. So what was monitoring at Databricks like before M3? First, I'm going to provide some context about the role that monitoring plays for Databricks engineers. We have 2 main metric sources. The first is our internal services that run on Kubernetes clusters that we manage in-house. And then we have external services running co-located with the VMs for customer Spark workloads, and these run in customer environments. We've been running a Prometheus-based monitoring system to monitor these targets since 2016, and all service teams rely heavily on the system. Service owners write and emit their own metrics from their own services, and they use these metrics for dashboarding. We use Grafana for dashboarding, and they write their own queries. And most engineers are PromQL literate, and engineers maintain their own alerting rules. Some of the use cases we have are real-time alerting, debugging, SLO reporting and alerting, and automated event response. So yeah, to sum it up, monitoring is a pretty critical workflow for engineers at Databricks for their services to run smoothly, and it's core to our engineering culture. So this is what our original Prometheus monitoring system looked like in one region. So for those of you who are not too familiar with Prometheus, it's a single node monitoring solution that is used for event metrics and alerting. It uses like a pool-based model, and it will scrape metrics from other services. And it stores these metrics as time series data, and then it can service queries and alerts using this data. So in each region, we have 2 different prompts for the 2 types of monitoring targets that we have. The first prompt is Prometheus normal. This is the instance that scrapes all the Kubernetes pods local to the cluster. And then we have a Prometheus proxied instance for proxied metrics from services that live outside of our Kubernetes cluster. In particular, we use like a push-based path through Kafka or Kinesis to get these metrics into our metrics proxy service, which runs in our Kubernetes cluster, and then this is then scraped by the Prometheus proxied instance. For this Prometheus instance, we maintain a whitelist to only ingest some metrics so that we can reduce metrics volume, since the metrics from our customer environments are the higher cardinality workloads. And the reason we have 2 separate Prometheus servers instead of just 1 server per region is because of scaling limitations. And we found that metrics from both of these sources would not fit on a single Prometheus server. So though it's not ideal to have separate servers in one region, there's kind of a logical separation between these 2 metric sources, so engineers can still function pretty well with having a sharded view of metrics per region. Each of these Prometheus servers are set up in a high availability blue-green deployment so that we can in place update one of the Prometheus servers while the other is still running and serving alerts and queries. We also have a disk attached to each Prometheus server to store metrics. We have a global Prometheus server, which contains a subset of metrics federated from the regional Prometheus servers across all regions. For this, we're just using the out-of-box federation feature from Prometheus, and we also maintain a whitelist here, so we only federate some metrics that users need to have if they want like an aggregate view of their services across regions. So users interact with this monitoring system in 2 main ways. The first is alerting. So each of these Prometheus servers will evaluate alert rules and issue alerts to Alert Manager, and then Alert Manager will forward the alerts to the end response channels like PagerDuty or Slack. And the second workflow is querying or dashboarding. So users can query the regional Prometheus servers to view the metrics from their services or any metrics like underlying alerting incidents. And typically users will mostly interact with just a regional Prometheus, but when they need like a global view of services across regions, then they use the global Prometheus server. So here are some numbers to give you a picture of the scale that we were running this Prometheus monitoring system at. We ran in more than 50 regions and different cloud providers, and we monitored like 100 plus microservices with an infrastructure footprint of 4 million plus VMs of Databricks services and customer Apache Spark workers. And because of our architecture, where we had a single Prometheus server handling all the metrics from the customer environments, that server was pretty huge. Like at its peak, it was handling close to 1 million samples per second, had a pretty high metric churn rate with a lot of metrics from short-lived Spark jobs persisting for like less than 100 minutes. And the disk usage was pretty high at 4 terabytes for only 15 days of retention. And we also were running on a really big machine with 64 cores of CPU and 2 terabytes of RAM. At this scale, we found our Prometheus system extremely difficult to operate, and we found that it also impacted on the user experience. So for us as the operators, we had to handle a lot of capacity issues like frequent and a lot of high disk usage situations where we had to resize a disk. And also we had to deal with multi-hour prom updates because of the long write-ahead log recovery process during restarts. In terms of the user experience, users had to deal with like a sharded view of metrics. They had to be like aware of which metric source they wanted to query, whether it was prom normal or prom proxied. Users also had to deal with slowness of querying. Big queries would take like a long time. Sometimes they would never even like complete, and sometimes they would even cause the Prometheus server to We also had to build a custom querying UI since the out-of-box Prometheus UI was too slow to handle high volume. Users also had to deal with shorter retention period, and they could only see metrics in like the last 15 days instead of the last 90 days, which was ideal. And they couldn't really see metrics spanning across different release cycles since our release cycle is only 2 weeks. And also users had to deal with a metric whitelist. They could only include a small subset of metrics in the whitelist. And occasionally for us as the operators, when we were dealing with like capacity issues, we would even have to actively remove metrics from the whitelist. And then just to keep our Prometheus server running. So with these scaling bottlenecks and pain points, we really needed to find a more scalable monitoring solution. Some of our requirements were the system needs to be able to handle high metric volume, cardinality, and churn rate, since Databricks was growing rapidly and we needed a system that could keep up. We also wanted there to be a 90-day retention so that engineers can monitor their service release over release. Also importantly, we needed it to be PromQL compatible since everything is already built on top of Prometheus, so we didn't want to migrate user workflows like alerting rules, querying, or dashboards to another system and teach users to use a different language. Also, we needed the system to have a global view of metrics so that engineers could have the ability to have an aggregate view of important service metrics across all regions. And finally, the system needed to be highly available. Some features we considered like nice to haves were first, ideally it would have a good update and maintenance story without some of the pain points that we experienced with our Prometheus setup. So like no metric gaps during updates and less manual operations for updates. It would also be nice if the system had been battle tested in a large scale production environment. And also good if the system was open source so that we have more freedom to manage it on our own to make it more suitable to our metric workload. And also we felt that there was more transparency into the cost of running an open source monitoring system. Some of the alternatives we considered in mid-2019. Firstly, we considered sharding Prometheus even more, but we were a bit hesitant about this because it was more of like a do-it-yourself situation and not an out-of-box scaling solution. We considered some open source solutions like Cortex and Thanos. We prototyped Thanos in late 2018. At that time, it wasn't that mature back then, and we weren't really comfortable using it at our scale in production. And we also prototyped Cortex, and we found that it wasn't really suited for metric workloads, which had a pretty high churn rate. We also considered some hosted solutions like Datadog and SignalFX, but they were too expensive. So given our requirements and the alternatives we considered, why did we pick M3? M3 fulfilled all our hard requirements. It was designed for large-scale workloads and it's horizontally scalable, and it exposes a Prometheus API query endpoint as well. It's set up to be highly available with a multi-replica setup, and it's designed for a multi-region and cloud setup, which is perfect for our use case and has a built-in global querying feature. An important point also was that it had been battle tested at high scale at Uber in a production environment where it had been running for a couple years. And also an added bonus was that M3 has a Kubernetes operator for automated cluster operations, like scaling the cluster or updating the cluster. And also we thought there were like some pretty cool features that we would be interested to use in the future, like aggregation of metrics on ingest and downsampling of metrics, which could potentially allow us to have a longer retention period. So now I'm going to cover how we deploy M3 at Databricks, like specifically the different decisions we made along the way and how we arrived at our final architecture. So our initial plan was for M3DB to be a drop-in replacement for Prometheus local disk storage. So instead of Prometheus servers storing metrics in an attached disk, it would remote write the metrics into M3DB for storage. Prometheus servers would still be evaluating alert rules, and they would remote read metrics from M3DB to evaluate these rules and then forward the alerts to Alert Manager. So this setup would result in some improvements. First, since all metrics would be remote written into the M3DB storage database in the region, we would get rid of the sharded view of metrics in one region. So users could have a consolidated view of both prom normal and prom proxied in one region, rather than having to query both separately. We would also not have to maintain a global Prometheus server anymore, since M3DB has a global querying feature and it can connect with other M3 clusters in other regions to provide the global view of metrics across all regions. So though this architecture was really simple and it would have been the least amount of work to incorporate M3DB into our system, we did find like some trouble with remote writing from Prometheus servers. Like specifically, we couldn't remote write at the scale that we needed, especially for this Prometheus proxied instance, which was handling all the higher cardinality metrics from our customer environments. So now our question was, how do we scale up the write path successfully? To make it work, we needed to move away from having two giant Prometheus servers and instead make the metric remote writing path a lot more lightweight, handled by many small components rather than fewer larger components. We found a solution to this in the Grafana agent, which is open source by Grafana. This is a lightweight component that is Prometheus API friendly and solely functions to scrape and remote write metrics. There are many instances of this running in our cluster, and we shard the scrape targets and assign them across the Grafana agent instances. So this makes it really easy for us to scale the metric scraping and remote writing path, since to do that, we just need to increase the number of these agent replicas and then reassign the scrape targets accordingly. Also, for metrics coming from outside our Kubernetes cluster, from our customer environments that were proxied through our metrics proxy service, we added a remote write protocol into the metrics proxy service so that it would directly remote write metrics into M3DB. So this saved us from needing to have another set of Grafana agents scraping the service to handle metrics coming through this path. And it just overall reduced the number of hops and the end-to-end latency of the metrics being proxied from outside our Kubernetes cluster. So now we kind of solved the challenge to make the write path scalable, but we needed to find a way to evaluate alerting rules since we weren't using Prometheus servers anymore. So unfortunately, M3 doesn't have an out-of-box rule evaluation engine. It mainly just serves as like the metric storage database for writing to and querying from. So this led us to building our own rule engine. This was more like in the spirit of designing an architecture with more lightweight and scalable components, each serving a more narrow purpose. So for this, we ripped out the rule management code from open source Prometheus and deployed that as our Prometheus API-friendly rule engine. So we pass our original Prometheus monitoring systems alerting rule configurations into it. It issues alert rule queries to M3DB. M3 handles the rule evaluation and evaluates the query, and then it returns the query result back to the rule engine. The rule engine does some extra like processing for checking, for example, the for duration of the alert. It adds like any extra external labels to the alerts, and then it'll issue the alert back to the user. So far we've covered the components we set up to interact with M3, like the scrape agents, the metric proxy service with the remote writing, and the rule engine. Now I'm going to focus more on what our M3 setup looks like. So basic setup of M3 will typically have like two main components. It has the storage cluster and the M3 coordinators. The storage cluster consists of multiple replicas. In our case, we use 3, and each replica has multiple pods, and each pod has a disk attached to store metrics. To scale up the cluster, we just increase the number of pods in each replica. And then we have the M3 coordinators. These allow us to interact with the storage cluster to read and write metrics. The coordinators have M3 query embedded in them. So for write requests, it receives the requests, unpacks them, and then writes them into all replicas of the storage cluster. And then for read requests, it will receive the requests, fetch metrics from the storage cluster, evaluate the query, and then return the query results back to the client. We also run the M3DB operator. This is like optional to have in an M3 system, but it was like we use it because it's really useful for a Kubernetes setup. Since it automates scaling up and down the cluster and also automates like deleting and creating the storage cluster. So we don't have to manually manage the 3 different replicas. One issue we did have initially with this basic setup was that the M3 coordinators were having a lot of like noisy neighbor issues. For example, if a user submits a heavy query, it might like take up all the CPU and memory on the coordinator, and which might impact the write path and cause data loss, or impact the rule evaluation workload from the rule engine and affect the availability of alerts. So to make our M3 deployment more stable and have more isolation between writing, querying, and alert evaluation workloads, we decided to create separate deployments of the coordinators for different purposes. So in M3, read and write workloads are quite different for the coordinator. Writing is more CPU intensive since coordinators need to handle and unpack many incoming write requests. And reading is more memory intensive since they need to fetch and store cache data in order to evaluate and serve queries. So we created 4 different groups of coordinators. We have a group that handles writing. These consist of many small replicas of write coordinators to handle any incoming requests from our scrape agents and the metrics proxy service. And then we have a group designated to the rule engine. This just handles like a regular and more predictable workload of querying for rule evaluation, since the rule engine will just submit the same set of alert rules at regular intervals to M3. And then we have 2 groups here to handle ad hoc querying. The first is the regional group. This just returns query results based on the metrics in the regional cluster. And then we have the global querying group, which reads from M3DB clusters across regions and provides a global view to our users. We wanted to separate the regional and the global coordinator groups since the global coordinator group, the configuration is really different. It requires setting up listening across clusters and has different security configurations. But more importantly, our users mostly only use a regional view of metrics in most cases. And so since we knew if we just exposed the global view, it was unlikely that users would be like making the extra effort to always add a region label filter to each query. We wanted to provide a default region-only querying endpoint to avoid creating the extra cross-region traffic and cost for no reason. So now that we separated the coordinator groups, our 2 most important stable workloads, the write path, where stability is important to prevent data loss, and the rule evaluation path, which is highly critical for us to always have alerts. These workloads were isolated from the more spiky and unpredictable workload of ad hoc queries, where it's subject to bad behavior from users. So the final challenge was, how can we monitor all of these M3 components since there are so many of them and still avoid like a circular dependency where we're using the same system to monitor the system? So for this, we decided to set up a vanilla lightweight Prometheus server. This Prometheus server only scrapes M3 related components. It has no disk attached and its retention is only a couple of hours. So it's very easy to maintain since we consider it to be stateless and restarts happen really quickly. The metric retention period is short, but it's sufficient for us since we mainly use this Prometheus to alert us if any M3 components are down. And it doesn't really require us to look back on metrics over the past couple of days for this Prometheus server to issue alerts. And it issue alerts straight to Alert Manager and doesn't have like, it's completely independent from the M3 system. We also have a global M3 monitoring prom for a longer term view of our M3 related metrics. For example, to track disk usage or memory usage or like the number of reads per second. And we use the prom federation feature here to federate all metrics from the regional M3 monitoring proms to be persistently stored in this global prom. So this global prom has a disk attached, and also we run it with the blue-green high availability setup. And the main reason we use Prometheus here instead of just running a separate M3 cluster to monitor M3 is because Prometheus is a really good all-in-one kind of out-of-box solution for monitoring, especially at a small scale. And we felt it would be overkill to set up a separate M3 cluster with all of its like small components just for this use case. Also, we're more familiar with Prometheus since we've been using it for a couple of years now. And also Prometheus has been around for longer in the community. And we felt that we wanted to be comfortable with something if we were monitoring M3, which is a relatively newer system. So now I've covered how we deploy M3 and our architecture, and I'm going to share more about how we did the migration from our Prometheus system to the M3 system. So there are four main steps in our migration. The first step is bringing up the whole M3 system as a shadow deployment. We were dual writing metrics to both Prom and M3 storage, and we were evaluating alerts in both the old Prometheus system and the new M3 system. So we just sent all our alerts from the new M3 system to a black hole receiver that didn't fire alerts to any real receivers. And we also opened up a querying endpoint, but only internally to the observability team and not really to the rest of engineering or the eng org, so that we could do some behavior validation. So the second step of behavior validation is we compared alerts across the two systems by using scripts. And we also did some querying speed and correctness checks by comparing our more like well-used complex dashboards side by side. The third step was an incremental rollout of querying traffic and alerts. For ad hoc querying traffic, we staged it across environments, and we did a percentage-based rollout of traffic from Prometheus over to M3. And then for alerts, we did a per service migration. We replaced alerts emitted by Prom with alerts emitted by M3 for less critical services first, and then we moved on to more critical services in the later stages of the rollout. And the final outcome of this rollout is that all ad hoc querying traffic and alerts are served from the M3 system, and then we can safely deprecate Prometheus. So here's a diagram to illustrate like how we did the rollout of the ad hoc querying traffic. It's a pretty simple setup. We just put an M3, an Nginx in front of the querying endpoints of Prometheus and M3, and we split the querying traffic across both. And over time, we just slowly increased the percentage of traffic directed to M3. This strategy was pretty good for us to give an idea, give us an idea of how ad hoc querying traffic affects the utilization in the M3 system. And we did end up doing like some tuning of querying limits and extra provisioning of resources up front as we did this rollout to make sure that the rest of the rollout would be smooth. And this is a picture to highlight how we did the per service migration of alerts. So all our alerts at Databricks are emitted with a service label, which denotes the service and the owning team they belong to. In addition to this label, we added a source label to indicate whether the alert was emitted by the old Prometheus system or the new M3 system. And then we made some routing configuration changes in Alert Manager so that if we want to roll out M3 alerts for a less critical service first, the M3 alert from that service would go to the receiver, but the equivalent Prometheus alert for that service would go to the black hole receiver that doesn't alert anyone. We found this rollout strategy to be like really nifty because it was all controlled in Alert Manager at the routing level. So an Alert Manager can hot reload any new config quickly without any restart. So it was very easy to advance the rollout, but more importantly, it was like easy to roll back if we found any issues. And this was good to do since alerting is a highly critical service, so rollback should be able to happen quickly. Yeah, the outcome of this one-year migration is that M3 now runs as the sole metrics provider in all environments across clouds. The global querying endpoint is available via M3 for all metrics. This is still in beta, so we're still like testing this and rolling it out. And the user experience is largely unchanged. Our users still use PromQL for alerting rules and dashboards, and we still use Alert Manager for all our alerts. Retention is widely 90 days across all regions, and this is unlike before where we had our large Prometheus server, which had like 2 weeks of retention. And overall, we think that migration went pretty smoothly. We avoided any major outages since we had a good rollback strategy. So now we have much higher confidence that we can continue to scale this system into the upcoming years, since Databricks is like continuing to grow rapidly as a company, and it will keep processing larger and larger workloads. And most importantly, the observability team doesn't have to deal with like a giant Prometheus server anymore that runs on 2 terabytes of RAM and takes like multiple hours to restart. Okay, on to Nick for lessons learned.
Yeah, thanks, Wai. I was having some sound issues earlier. Hopefully it sounds okay now. Can let me.
Yeah.
Awesome. Thanks, everybody. Cool. So I'm going to go cover some of our lessons learned in operating M3 over the past year or so. Some of the things I want to talk about are some of the system metrics that you should be looking at if you're monitoring M3, give some general operational advice, talk about some things that we found it really helpful to alert on, and also talk a little bit about how we do upgrades and updates. I just want to give a brief overview because when you're talking about sort of like from the trenches, I think the perspective can sometimes sound negative because I will be talking about issues that we've run into. But I want to like emphasize at the start that overall M3 has been amazingly stable for us. YY sort of talked about how much trouble we had operating Prometheus. It was a constant source of alerts and trouble for us, and we operate more than 50 different deployments of M3, and it's just really stable. We have a few places where we've run into issues, and I'll be talking about those. And those are obviously the ones that have sort of the highest scale where you're really pushing against the limits of what we can do. But overall, it's been an extremely stable thing for us. And honestly, the biggest problem we have is just that we keep running out of disk space in places because our metric load keeps going up. And that's not obviously M3's fault. That's our fault for needing to be better about how we deal with incoming metrics. So even though that's the positive side, we have had some problematic things. So I'm going to dive into that because dealing with problems is obviously an interesting thing to hear about. Before I do that, just a little bit more about how it runs. Like I said, we have a large number of clusters, so we have to automate things. We use a combination of Spinnaker and Jenkins to do template applies to update things. So that's where having the operator is really nice because it makes it pretty easy to kind of do those updates. In our bigger clusters, we process close to 1 million samples per second and about 200,000 reads. So we are more write heavy. That's definitely the workload that we have at Databricks. Cool. So I wanted to jump into sort of at the top level the things that we found most important to keep an eye on while you're operating. So we look at how much memory is being used. These are in the M3DB pods. We have seen that if you're steadily over 60% of memory usage, that can be bad. Mostly because there are certain things that happen that can cause memory spikes. And then if you're consistently over 60%, those can get you all the way up to over 100%, and then you it's nice that because it's distributed and highly available, if only one pod ooms, it's not a big deal. It recovers. Nobody even notices. We don't even get alerted when that happens for a single one. But if all of your pods are consistently over 60, you have a good chance of multiple ones ooming, and then things can be bad. So how can you resolve that? If you're steadily over 60%, you can scale up your cluster, or you can reduce incoming metric load. Those are the two primary ones we found. Obviously, if you're in a more read-heavy workload, you may need to do something like reduce the amount of reads that are happening. One thing I'll mention here with the new version of M3 having all these nice limits for reading and writing, it's really a great other way to sort of put limits on the memory use. So we've already done that, so that's not a way we resolve these, but if you haven't set the limits, that would be another way to try to reduce the amount of memory. And I've included here, you obviously don't need to like memorize the queries that I've put in here, but I've just kind of put them in here as a reference for like the way that we look at these. So we look at this particular metric filtered for our pods. We also need to alert on disk space. Like I mentioned, this is a problem for us just because as things grow, the cluster can get bigger and bigger and your disks can fill up. We use predict linear to look at how big the disks are. The disk space usage is actually a very easy to predict over, so it's pretty accurate. And so we do it very early, mostly just to give ourselves lots of time to react. There's other things going on. Sometimes it takes a little bit of time to get to it. And also, we've found that scaling up can take a significant amount of time in the really big regions. And so it's nice to give ourselves enough time to deal with this. And again, ways you can fix this if you are running out of disk space or scaling up the cluster. Like I said, reducing retention obviously will free up some disk space, or reducing the incoming metric load. And again, here's the query. Like I mentioned, cluster scale up can be slow. There has been a good amount of work in improving this bootstrapping time in the newer versions of M3. We are a little bit behind on the update schedule, so we're hoping to see some improvements in our cluster scale up time as we upgrade to the newer versions of M3. But I would encourage you, if you're operating M3, to try to do some testing around how long it takes to do this cluster scale up, so that you can set the sort of limits and like how long in the future you need to alert for these kinds of things, so that you know how to react to them. Cool. So that was some of the those were probably the most important things that we need to alert on. I'll get onto some of the other smaller things in a little bit, but I also wanted to give a little bit of general advice that we've kind of accrued over the time over operating M3. One thing is try to not add a lot of custom annotations, labels, configs on top of the deployments. The operator does have certain expectations about the stuff it's going to deploy, and we've shot ourselves in the foot a few times by trying to do weird custom things, and then the operator can get confused, or we can get confused. And anyway, if possible, avoid doing lots of custom things. Let the operator just do its thing. Like I mentioned, do observe your query rates and set limits. So look at how your cluster is being used in a good state, and try to set limits so that you can prevent a bad state from occurring if giant queries come in, or things like that. One thing that I think we waited much too long to do at Databricks was to have a really good testing environment. Meaning we rolled this out in all of our clusters, and it was working pretty well. But a monitoring system is something that everybody relies on all the time, which means that your dev clusters are development for other engineers. But for us, our dev clusters are actually quite important to have good monitoring, because people care about observing how their test clusters are running. And so we needed sort of a dev, I guess, or a M3 dev cluster, which we now have, but it took us too long. But it was really important. I think it's important to have a place where you can quickly iterate on rolling out new versions, testing load. Important to be able to just throw away the data there, so that if you're testing some stuff out and it doesn't work, you're not scared of ruining your data. And I think it's also important to try to have that at scale. And this is non-trivial, having load generation and stuff, because if it's truly dev, you're not going to have a lot of stuff running there naturally. So there is some work to doing that, but I think it's very valuable to have this so that you can kind of be aware of how your production clusters are going to behave. But not be testing it in production, because if you're only testing high load in production, it's not a recipe for great success. I also would encourage you to have a look at some of the M3 dashboards that are out there, and kind of learn what these metrics mean. It can be really helpful. As Rob mentioned, M3 has a ton of features, and it also, as a metricing system, has a lot of its own internal metrics. The dashboard I've linked here is kind of the one that the M3 webpage mentions. I would say that this one that's linked here, at grafana.com, is somewhat developer focused. I think it's built to help people who are working on M3 understand what's happening and debug issues, and that's useful for that. But I would maybe suggest kind of looking through that and understanding what some of the more useful metrics are from an operational perspective, and making a dashboard with your own key metrics. I'm not going to cover that. This is for future reference, this is what one of our internal dashboards looks like. So we kind of look at a lot of the more high level things that kind of show, how's CPU doing, how's memory doing, and you can kind of see in that memory one how it's it goes up and down. But we try to keep it, at about the 50% to 60% level of what's available. And I'm not going to cover all the other stuff that's on here, but basically these are some of the things that we have found really useful to monitor in terms of understanding what's happening from a more sort of operational perspective than this sort of really internal perspective of a developer working on M3. Cool. So a few other things that we alert on, just that things that are worth looking at. So if we have high latency ingesting samples, so this is the coordinator ingest latency bucket metric, that can mean that you're just getting backed up in writing samples, or that there's some other problem with the incoming metrics. We do try to filter on the incoming metrics and prevent them from coming in late, but I will say that although the Grafana agent has been pretty good for us, one problem it does have is a tendency to sometimes try to write old data, and it's hard to get it to not do that. So you can sometimes see spikes in this from that, and then you need to go kind of kick the agent to have it not do that. We look at the rates of both write errors and fetch errors. These are good ones to be watching, mostly because they kind of represent the user perspective. They say like, how is it as a user of M3 trying to do something like write a metric in, or trying to do something like issue a query, am I seeing errors, right? There can be all kinds of other errors happening under the covers, but if these two metrics are steady from a user perspective, you're kind of okay, you're meeting your SLO. So we monitor those. And those ones kind of issue some high priority alerts. If you're getting write errors, something's bad, you're not able to write metrics into the cluster. If you're getting fetch errors, something's bad, you're not able to query the cluster, and your users will be seeing issues. Another one that we monitor, and I wanted to mention this one because it can cause, for us, it can be a really big issue, but it may not be depending on your deployment, but we do look at how many out of order samples are being written. And the reason that we do this is because if you are double scraping pods or services, that can cause all kinds of craziness in your metrics, because they can kind of bounce around, and the counter semantics of Prometheus make it think that crazy stuff is happening. And because we operate in a largely pull-based architecture, this can cause a lot of false alerts for our customers. It is a little bit of a tricky one to monitor, because some amount of out of order merging is expected and doesn't mean that there's a problem. So I put an X here because you'll probably need to look at how it looks in your cluster. And another thing to be aware of is that during node startup, there can be a little bit more out of order merging, just because there may be some data that's sort of built up and things are not coming in directly in order. So you'll want to inhibit this during node startup. But if in sort of a normal operation, you should be able to get a good sort of baseline for what your out of order write rate is. And then if that spikes, it can be indicative that you've somehow messed up the configuration of your scraping. Yeah, so that's another one that has bitten us. Great. So talking a little bit about upgrades and updates. They have been, I think Rob mentioned that they do really focus on, or M3 really focuses on having good forward and backward compatibility. And we have seen that, we have experienced that. We are not scared of doing updates to new versions. We have not seen really any issues. I only mention this because it's literally the only issue we've run into, is just there was a tiny query evaluation regression where I think they changed something in the query engine. And it was also relatively, it was not a big deal and was fixed relatively quickly, but we've been running M3 for a while through a lot of the early pre 1.0 things. And so there were a relatively large number of updates there that we've gone through, and it's been very smooth for us. So that's been great. We are now just moving into 1.0 slowly throughout our clusters. That has also been very smooth. Rob kind of mentioned that there were some config changes and made it sound like it's a big deal, but honestly, there weren't that many config changes. We have a pretty complex kind of programming system for generating our configs, and so it was pretty easy for us. I suppose if you have manual configs, it might be more work, but for us, it really wasn't a big deal to update to 1.0. One thing to be aware of, there were some sort of API changes. So this is probably only relevant if you have built up sort of institutional knowledge around M3 already, but a lot of our runbooks we had to go through and change some of the API paths that we say to hit for things like changing retention or updating placements. That's sort of like advanced usage. So as a normal user of M3, you probably won't run into any of that. I mentioned that we manage all of our upgrades and updates via Spinnaker and Jenkins. The one sort of minor issue here that we have is up until now, there has been a lack of fully self-driving updates. We kind of count, we're a very bought into Kubernetes shop, and we kind of account on our pipelines being able to do updates by just calling kube control apply on a new template. This was not fully working until recently, but as Rob mentioned, with the 013 version of the operator, this should now be available. That's a relatively recent release. We have not had time to go fully test this, but we do believe we'll be able to move to this in the near future. One thing that I would want to mention, if you are doing these kinds of fully self-driving updates, or sorry, if you're not doing fully self-driving updates where you are just applying and then having to do some kind of manual intervention to get the operator to do the update, we have to be vigilant that the configs, which can be updated by just calling kubectl apply, stay in sync with the M3DB version. We've had some issues where our pipeline goes and deploys new version specification and new config, but the old version is left running, and then we restart it and it's like, I don't understand this new config. So that's one thing to be careful of. And then one suggestion I will have, this is probably generally good, but it's one that we found really important during the upgrade process, is to have a readiness check for your coordinators. So try to make sure that your coordinators, as they come up, are able to talk to M3DB. And then, I'm not going to cover sort of update strategies for Kubernetes, but if you're familiar with Kubernetes, have like a rolling update strategy that doesn't restart too many coordinators at once. What we found is that if you run a lot of coordinators, these coordinators are super lightweight, which is great, and we run a whole bunch of them. But that means if they all restart quickly, which is what happens if you don't have a readiness check, it's so many services restarting that Kubernetes has a little bit of trouble dealing with the churn, and can leave a number of the coordinators unable to connect to M3DB, just because it hasn't had time to sort of update all the endpoints and the various service updates that it needs to make to do that. And then you have like a little bit of downtime. And because the Kubernetes control loop is not super fast, it can actually just take a while before it sort of churns through and updates everything. So having this readiness check, if you have a connect consistency on the coordinator, then that will sort of enforce that the coordinators restart slowly and reestablish their connection before the next one goes down, and you can have sort of zero downtime updates. Cool. So that's what I wanted to mention about upgrades and updates. And then just a little color about metric spikes. In any high volume system that you operate, you're going to have a way to deal with spikes. An example of something we sometimes have is somebody goes and adds a new label to a metric, and it has an absurdly high cardinality. So suddenly your number of time series is just going up by a huge amount. This happens. You don't control all the services that get deployed. They can do crazy things. And so a great way to deal with this is, you need to be able to identify where it's coming from. So, have some metrics that you can look at that cover, the Grafana agents can expose this. We have our own metrics inside our other systems that sort of push directly into M3. So always have some metric that you can use to see, who is producing all of these metrics. And then also be able to cut that source off easily. So we have good ways of sort of quickly blacklisting things, because this is extremely preferable to ooming your cluster. I'm much happier to be able to go to a customer and internal customer and say, hey, your service is now currently not having any metrics because you did something silly, rather than having to send an email out to the entire company and say, hey, our metricing system is down in production right now. It's never a nice message to send. So yeah, that's something I would recommend. So just a little bit about how we do capacity. Obviously, I think it's going to depend a little bit on your workload. So we found that about one M3DB replica per about 50,000 incoming time series works pretty well for us, but we are very write heavy, so that may be different depending on how your cluster looks. I saw that there was a question about how many nodes we use on that big cluster. We're currently running about 18 nodes per replica, so you can do the math for how many we have altogether. And we run about 50 write coordinators in 2 different deployments, so about 100. And like I said, we just are happy to run lots and lots of these for stability. We probably could get away with fewer, but this just gives us sort of the buffer that we need, and it's okay. And these are just sort of numbers that we've come to sort of organically. So I don't have it would be nice if I had sort of a formula like this many in do this many things, but I think partially also just testing, and because it will depend on your workload. Cool. I did want to talk a little bit about some of the things we want to do in the future. So I would say at this point, we have completed fully completed our migration away from Prometheus. We are removing Prometheus everywhere. So we don't need it anymore, aside from these sort of like lightweight monitoring ones that YY mentioned. And we're now getting to the point where we can sort of look towards the future and what nice new things that we can do. So we were sort of previously we were in this bad state that Prometheus kept crashing and everything was unhappy and it wasn't good. And we've, had a very successful but somewhat long migration also to now have a sort of stable set of monitoring clusters running. And so now we can start to look forward and say, hey, now that we have this nifty new M3 thing, what can we do? And so some of the things we're looking to do in the future are to start getting downsampling for our older metrics. So this is something that we expect to see significant savings in disk space, probably also in query performance over older data. We run with a 30-second scrape interval, and it's a little bit unreasonable to expect that when you query data that's 60 days old, that you'll get it at 30-second resolution. We will be looking at using different namespaces for metrics that have different sort of retention requirements. So like I mentioned, we run a lot of test things in our dev clusters. It's a bit unreasonable also to expect that these test clusters will have really long retention on their metrics. So a really nice feature that M3 has is that you could kind of put those metrics in a different namespace and then have a shorter retention on that namespace. So your test clusters get 5 days or whatever of retention, and that's great. And then for things that matter more, you can have longer retention. Again, this is to deal with less needing less disk space, lower load on the system. And then another one that I think we are excited about that M3 has enabled, because M3 supports sort of pushing metrics in. It allows us to do to enable work use cases where you're in a mode that's actually very hard to be scraped. So there's things like Databricks jobs that we leverage, where Spark clusters are running and processing lots of data. Our data science teams really want to track those jobs, and historically it's been very difficult because those jobs are running sort of somewhere else in an isolated cluster. And how would Prometheus reach over there and scrape the metrics out of it? And so being able to sort of build a little proxy so that they can push metrics directly through into M3 is really great. Another one that our dev tools team is looking at is they want to sort of monitor things from developer laptops to know, hey, how long is it taking to do certain developer operations so that they can improve the developer experience at Databricks. And they want to also be able to push metrics in, because obviously your scraping system is not going to be able to reach out and scrape metrics from your developers' laptops. So that's another feature that M3 has that's sort of like a new thing that we can do. There obviously are ways to push metrics into a proxy for Prometheus, but we found them, we did operate some of those, and we found them to be less than reliable just because of the nature of kind of needing to cache the data and then re-scrape it. It's much less reliable to do that than to be able to just directly push the metric in. Because it lets you, caching is just a difficult problem with metrics. So I'll leave it at that. I've spent a lot of time trying to fix various metric caching issues. Anyway, so I want to leave a little bit of time for questions. So I'll just conclude, and then we'll leave about 10 minutes. So I would say, in conclusion, this has been a very successful migration for us. We were very happy with where we've landed overall. The community has been extremely helpful. We've worked a lot with the people at Chronosphere who have been extremely helpful. We've worked sort of just with the open community as well, and people. It's been a great experience there. And there's a lot of great new things sort of on the horizon for us, and we're really excited to be sort of shifting gears into making the overall metrics experience at Databricks better from a sort of feature perspective, not just from a stability perspective. So cool. That's what I wanted to say, and I think we can maybe shift to questions. So I see a lot of them have been marked as answered, but okay. So let's see. I see why Cortex didn't suit the high churn rate. We didn't dive very deeply into this, other than that we did actually talk to the name is escaping me right now, but the main guy who started Cortex at Grafana, and he did kind of identify this problem that Cortex has with ingesting a lot of sort of short-lived metrics. And so, and I see that YY would like to answer this question live, but
Oh, I just clicked it for you.
oh, okay, thanks. So that is something that we kind of ran into, and we actually did try quite hard to deal with that. And then how many production issues are we facing daily on over 50 clusters? If I exclude disk space issues, I would say we average maybe 1 or 2 a week of actual production issues on over 50 clusters. So like I said, it's really very stable at this point. Something I would say probably the main thing we are focusing on right now is kind of getting a handle on the increasing load. Databricks is scaling very quickly in terms of how many people use the platform. And so our metric loads just continue to go up. And so we get a lot of alerts that sort of say, hey, you're going to be running out of disk space. And then we have to kind of decide, are we going to reduce retention here? Are we going to try to scale up the cluster? Are we going to go try to figure out like which are the worst offenders and make them reduce their things? So those are sort of a separate set of issues, mostly because they're not really, I wouldn't blame those on M3. That would be an issue no matter what system we were using. So in terms of sort of like M3 issues, I would say, on the order of 1 or 2 a week, and it's usually something like high memory usage or something like that. We also end up, with 50 clusters, there's inherently going to be some underlying infrastructure issues. So a lot of times it'll be, you've had some cluster where your node just can't schedule because there's some underlying issue with a cloud platform or something like that. But like I said, not a ton of issues overall. So hopefully that answers that one. How do you communicate with the community? Through the Slack channel? Yes. We have not taken the Chronosphere office hours. We may start doing that. But yes, currently our communication with the community has been through the Slack channel and through filing GitHub issues. I mentioned the operator self-driving thing. That's an issue that we reported that that there were some bugs in there, and they've now fixed those. So that's been good. So I would say our primary things of communicating are through the Slack channel, where people are pretty responsive, and also just through GitHub for sort of code issues. Node size using for the large cluster, I actually don't know off the top of my head. Why do you know?
Like around 100 gigs of RAM and 16 CPU, I think, something like that.
Cool. Oh, and someone noticed that I'm listening to Madlib. So yeah, that is a really good new album if you want to check it out. That's pretty awesome. Cool. And let's see. I saw that somebody else asked if we were wanting to open source our rule manager engine. And the answer is yes, we do want to at some point in the future. We do not have a roadmap for doing that right at the moment. But as soon as we sort of are able to prioritize that, I think that is something that we would definitely like to prioritize and get open sourced. We are a company that likes to open source things if possible. So yeah. Let's see. I don't know if I should go through. I see YY has answered a lot of these questions sort of by typing. So thanks, YY. Let's see if there are any other questions. Are we using stateful set disks? Yes. So we use a stateful set. We use SSDs under the covers. Like I said, we run across multiple clouds. One of the nice things about that is that Kubernetes can kind of hide some of those details for us. So we just have persistent volume claims that let us get disks for the clusters, and then they magically have disks, and it doesn't matter which cloud you're running in. Cool. Well, I don't know if there are any other questions. Otherwise, I think
We can wrap up.
cool. Great.
I don't know what a kill all bobber does, but that sounds fun.
Yeah, that was me trying to be able to stop sharing my screen, but now I still can't.
Thank you both. I'll hand it back to Gibbs, but yeah, that was, I hope that was like, I mean, yeah, extreme deep dives, and really valuable, I think, for everyone to hear about. So thanks for putting in so much work into it. It's really great to see under the covers for other folks out there running M3, obviously. So yeah, I just wanted to say, give a great thank you for all the detailed materials here.
Yeah, no problem.
Awesome. Gibbs?
Yeah, no, agreed. That was really great. Thanks both YY and Nick.